All right, guys, so we're going to try this a little differently. So we're going to tackle section 10.1 in parts. So this is going to be section 10.1. This is going to be part A. So this is going to be part A, and we are going to tackle what is a geometric series, and we're going to tackle it as a power series too. So we're going to kind of work our way through this. So what we're going to tackle today is we're going to tackle geometric series, and then we're going to talk about convergence and divergence of series. And let me shrink this down just a little bit for you guys. Get that away from there. There we go. And like partial sums kind of thing. So as we tackle this, we'll just talk about infinite series for a geometric series. Uh, so the idea is that when we deal with this infinite series here, you're going to, term one, term two, term three, and we just kind of work our way through it. You can rewrite that as the sum as k starts at 1 going to infinity of whatever function or expression we have here. And a to the n, we just talk about it as being the nth term. So kind of a quick little review there. Okay, so that's the idea of an infinite series. What's it going to do as it approaches infinity. All right, so now we just got to kind of come up with this idea of a series. And if you just kind of did this and put these together by grouping, you'd end up with 0, 0, 0. But that really doesn't give us the idea of an infinite series, because the infinite series, oops, that's a little bit of a mess. The infinite series uh, shows us that it's a1 plus a2 plus a3 plus a4, right? So if we do a1, that's going to be 2. And then we do a1 plus a2, that's going to become 0. And then we're going to do a1 plus a2, which is 0, plus a3, which is 2. So this thing keeps repeating itself over and over and over again. So the idea is, does it converge on a single number? Well, we don't know if it converges on 0 or it converges on 2. So since this infinite series limits as its partial sum, it has a sum, it has to be the limit. Well, we don't know what limit it approaches. It's either 0 or 2. So since it has no limit, uh, the series has no sum. Since it has no sum, it diverges. If it had a sum, it would be converge. It would be a convergent series. So you just got to work with the series based on the fact that it's a1 plus a2 plus a3. So we've got to work with that and repeat it to give us an idea. So an example of identifying a convergent series: does this series 7 over 10, 7 over 100, 7 over 1,000, you just work your way through it. Does this converge on a specific number? Well, if we look at it as they did, it's 7 and then it's 7, 7. So if we add those two together, we get 0.77. If we add the third piece in there, we get 0.777. And if we just keep going, 0.7, and then it's just going to keep going on 0.777. So this is going to approach a certain number, and that certain number is going to be 7 over 9, because 7 over 9 is going to give us this 0.77 deal. So since it approaches the sum of 7 over 9, because as this thing gets bigger and bigger and bigger and we add more and more sevens, it's going to approach this number here. So if that's the series, then it converges on the sum of 7 over 9. That's the idea of identifying a convergent series. So, so the idea is this. If you have an infinite series as such, and it converges, then the limit as it approaches infinity will equal 0. This means that if it does not equal 0, the series must diverge. Okay? So that's kind of the idea behind everything here. So let's kind of look at this here. I'm going to go, there's a notes handout that I gave you guys. So let's talk about that. So here's the idea. Infinite series are like our favorite here. So let's look at this here. So does, this is a big one, does 0.9999 equal 1? So we're just going to say, like they say here, S is equal to 0.99999. Well, if we multiply them all by 10, like it says here, 10S, and that equals 9.999. Well, this becomes a system of equations. Well, if we subtract these two, 10S minus S gives me 9S, and 0.9999 subtracted into 9.999 gives me 9. So when we subtract these two with each other, we end up with 9S equals 9, and we divide that by S. I'm sorry, we divide it by 9, and so therefore the idea of this series is that 0.9999 approaches 1. Okay? And so if we're really going to kind of think about that, 1 divided by 9 is 0.1111, 0.2222, 0.3333, 0.4444, 0.55. And as we work our way up, the question is, therefore, 9 divided by 9 is 0.9999, which is actually approaching 1. So it converges on a finite sum right here. Okay? It converges on a finite sum. Now, so that means we can deal with this geometric series idea where A1 is equal to 9. So A1 is equal to 0.9. So that's our A1. And to go to here, and if we go to each part of the series, we're multiplying by R equals 0.1. So the change is R equals 0.1. So what we end up with is 1 minus A1, our A1's here, divided by R. So we end up with 0.1 divided by 0.1 is equal to 1. So there's all these different ways to look at these series. Okay, this is based off a formula. This is based off a pattern. And this is based off of a system of equations. So there's 3 different ways to look at it. But we're going to work right here at this geometric series piece right there. We're going to work with that right there. So we know that this series has got A1, and then we're going to add A1 times R, which is up here is our 0.1, right? And then we're going to do A1 times R squared, and then A1 times R cubed, and A1 times R to the third. So the whole idea is that this right here is my final piece. Now, if we take this concept that we used up here, and I'm going to multiply both sides by R. So we're going to multiply this side by R and this side by R. We're going to get this extra piece here. We're going to get R times the series N equals, and then we got all this whole big piece times the R one more time times the series of n. So when you do that and you subtract 3 from 1 like we did up here, when we subtract 3 from 1, we're going to get everything to cancel out except these right here. So those are the only things we're not going to get to cancel out. This piece here, subtract this, all this stuff cancels out. This stuff cancels out here. All this stuff cancels out here, and we're just left with A1. All this stuff's going to cancel out, right? All that cancels out, and we're left with this, and we're left with that right there. So then we get this piece right here, and if I can solve for, I need to change colors for you guys because this is probably not working out. It's my first try. We'll see what happens here. So if we look at this, I have a common piece here. I've got my S of n right here. So I can factor that out. And if I factor that out, I get this little common algebra stuff here. And then let's make that darker. Here we go. So I can factor that out. And then where we go. We end up with this piece here divided by that piece there. So my equation looks like this. Right there. So from prior, we know that as the limit approaches infinity of this piece, it's going to equal 0. So if this piece equals 0, it's going to disappear. So we're going to end up with this equation. The sum of that series is going to be A1 over 1 minus R. And that's what we're going to be looking for, as long as it's between -1, as long as the ratio is between -1 and 1. So for the geometric series, it's one of our favorite ones here, because we can easily determine if it's convergent or divergent, but we can actually find out what it converges to using this. So we can look at it pretty quick based on that model there. So now that I've totally messed everything up, let's see what we got here. So we've got our geometric series here, and we have our idea that we have infinity. We've got the summation, or the series, from n equals 1 to infinity of times the ratio n to the -1. And so it converges to this sum if r is less than 1, and it diverges if r is greater than 1. Okay? So let's look at this here. Let's tackle this. So we're looking at this thing here, and we're looking at this. Here's our piece here. We know that the first term is a, so that's a is 5. Our ratio is 1/2, so it's less than 1. And so this series converges to, and we're going to use this formula. We're going to use A1 minus R. That's where this comes into play. So that sum of the series is equal to A to 1 minus R, and we just plug it in. It's going to be 1/2, and that's going to be 10. So it converges to 10. Okay, let's look at this one here. We got 3/5. That's our R. There's nothing in front of here, so if it's A times R to the n minus 1, this right here, there's nothing there, so A is going to equal to 1, which is really 3/5 to the 0 power. That's where they come up with this piece right here, okay? But that's no big deal because we know it's 1. We know the R is 3/5. We just plug it into it, and so it converges to 5/2. Okay? So that's our next setup there. So the breakdown here is this. We're dealing with geometric series that look like this, geometric series that look like this right here. So we are dealing with the sum of n equals 1 as it goes to infinity. And we're always looking for an A and an R times the n minus 1. If that's the case, the sum is going to be equal to A times 1 minus R if R is less than 1. That's the key piece right there. So that's what we're dealing with geometric series there. Hopefully this helps you guys out, and we'll gradually figure this piece out together. Good job. We'll talk to you soon.